Hello and welcome to the next class of Logistic Regression. We have learned how to measure the amount of association between two categorical features. We have also learned why linear regression is not applicable for modeling a categorical target variable. And we have seen what comes to the rescue when we want to predict a categorical feature. There are a few different methods of which we have learned of logistic regression in the last classes. We have also learned how to implement logistic regression using R. However, if you have noticed in the output, there are a few extra terms and there are few terms in regression which do not appear in the output of logistic regression. So let us try to understand the output of logistic regression in R. For that, I will use another new example so that we can explore one more example and at the same time understand how to interpret the output of logistic regression in R. So for that, I am going to use the S market dataset from the ISLR library. So I will make sure these two libraries are already installed on this device. And now I will attach these two libraries onto this R session. Now this is for a simple exploratory data analysis. I just want to find out what are the different features that are in the stock market dataset. I want to see its dimension and the 5-point summary of the different features of the stock market dataset. Of course, we can look at more details about the stock market dataset by looking at its help file. So as you can see, this is the data for the daily percentage returns for S&P 500 stock index between 2001 to 2005. There are quite a few features included in this dataset. Now, we may also want to see if there is any association between the different features of this stock market dataset. And as you can see, some of the features are a little more correlated than some of the other features. But overall, the amount of correlation doesn't seem to be extremely high for most of the features. Now, of course, we have removed the ninth feature while constructing the heat map because the ninth feature is the direction which only tells us up or down. So it's a categorical feature. And we may want to predict if on a given day the market will go up or down. So let us try to do that. So we will try to model direction, which is a categorical feature, on all the other features of this dataset. And we have already seen that there is some amount of correlation between volume and year. So it may not be necessary to include year in our model as of now. So that's what we do. We mention the different required features. We mention the name of the data set. And then we have to mention family equal to binomial. The logit link for a binomial family is the default link. So we may not need to mention it all the time. So this ensures that we are going to run a logistic regression. And then I also want to look at the summary of the output. So in the second column, I have the coefficient values, the regression coefficient values for the different features. Then I have the standard error, the Z value and the P values. Post that, there was supposed to be another column with a different number of asterisks which would indicate if any of these features are significant or not. As you can see, all the p-values are pretty high. So obviously, none of these features seem to be significantly affecting the upward or downward direction of the stock market. If we want to just extract the regression coefficient values, we can write coef and the name of the model. And this is our logistic regression showing up. So the law of odds of the direction can be modeled as minus 0.12, minus 0.07 lag 1, minus 0.04 lag 2, plus 0.01 lag 3, and so on. Now let us try to understand the output a bit more. So I have these p-values in the last column. Which hypothesis is it testing? As I told you, it is testing for the hypothesis beta equal to 0. What is beta? Beta is the regression coefficient. As you can see from the regression coefficient values also, they all seem to be pretty close to 0. And when we do the confirmatory test, which is the hypothesis test, there also we see that the p-values are not significant. Hence, we are unable to reject the null hypothesis, which means here we have evidence to support the null hypothesis, which is that the different predictor features are almost, the regression coefficients of the different predictor features are almost close to 0, indicating that these predictor features are not significantly influencing the upward or downward movement of the market. Now, what test is being done over here? The test that is being performed is called Wald's test. What is the test statistic? The test statistic is beta hat minus 0, which is the null hypothesis value that we are testing against, divided by standard error of beta hat. Now, in addition to that, I will write out the formula for the Wald's test statistic, and I will also introduce you to another test statistic, and we will discuss a little more about these different test statistics. But before we do that, let's take one more look at the output. We do not see R square or adjusted R square over here. Rather, we see two different quantities called null deviance and residual deviance. So, what are these two quantities? We'll try to understand that as well. In addition, we also see the AIC value, and the AIC value is the same Akai case information criteria which we learned in multiple regression as well. The AIC here has the same significance and importance in logistic regression. So, AIC and BIC, these are used as model selection criteria. The smaller the values, the better the model. And there is no benchmark value for AIC or BIC. When we have multiple models that we are comparing, we compare them against the AIC value, and the model with the smallest AIC value is considered as the best possible model. So, the AIC and BIC as criteria remain the same in logistic regression as we have seen for linear regression. The formula for calculating AIC and BIC also remain the same. So, let us now try to understand null deviance and residual deviance. What is a deviance? Deviance is minus 2 times log likelihood of the model, and lower the amount of deviance, better the model. Now, we cannot calculate R square over here because we are not calculating the difference between the fitted and the observed values. we evaluate a model based on the deviance, and hence there are two deviances that are given in the output: null deviance and residual deviance. In the null deviance, the model that is considered is the null model. And what is the null model? It's a model without any predictor features. Or in other words, it only has the intercept in the model. Now, as you know, we are not predicting y directly in logistic regression. Rather, we are predicting the log of odds. So, the null model essentially is this. And the null deviance is naturally minus 2 log likelihood of this null model. What is a residual deviance? Residual deviance is the deviance of the model that we are considering. So let's say we are considering a model with p predictor variables. Then the residual deviance is the deviance of this particular model. If we are considering all the features in the data set into our model, then that would be the full model. And residual deviance is minus 2 times log likelihood of this full model. The residual deviance tells us how well the response variable is modeled using just the intercept term. Residual deviance tells us how well is the response variable or the target feature can be modeled using the p predictor variables. Of course, lower the deviance, better the model. But if we want to know how much of an improvement is our model with p predictors, then we can calculate the difference between the residual deviance and the null deviance. This amount of difference tells us whether our model with p predictor features is a good model or not. However, good or bad can be subjective. Hence, we can do a hypothesis testing or a significance testing to make a more objective statement. And it turns out that this difference is actually a chi-square test statistic with p degrees of freedom. If this test statistic turns out to be significant, then we would consider this model as a useful model. So let us try to do that for the stock market dataset and also for the credit card dataset. So here for the stock market dataset, the null deviance is 1731 and the residual deviance is 1727.6. If we calculate the difference between these two, the difference turns out to be 3.6. Let's compare it with the chi-square value to calculate the p-value. As I have told you, the degrees of freedom is the number of predictors used in the model. So here we have used 6 predictor features in the model. I will write here p chi-square 3.6 df equal to 6 lower dot tail equal to false. So we see that the p-value for 3.6, which is the test statistic value, with degrees of freedom 6 turns out to be 0.73, which is obviously a much larger p-value, and this gives us pretty strong evidence against the usefulness of this model. So this model doesn't seem to be significantly useful over the null model. Now we can do the same thing for the default dataset as well. So this was the final model for the default dataset that we used. And here the null deviance is 2920.6 and the residual deviance is 1571. Of course, the residual deviance is smaller than the null deviance, which means this model with 3 predictors seem to be a good model. Or in other words, a useful model. But is it significantly useful? Let's find out by doing a chi-square test statistic. So first we will calculate the differences between the null and the residual deviances, and now we will calculate the chi-square p-value with degrees of freedom three. How is it calculated? So for our problem, it is simply beta hat minus 0 divided by standard error of beta hat. So we have seen in the R output that we have the beta hat values in the second column, the standard error of beta hat values in the third column, and the Wald's test statistic values in the fourth column, which is basically a Z test statistic. And then we also have the p values and the significance indicator. So this actually has the Z distribution under the null hypothesis. What is the null hypothesis? The simple hypothesis of beta equal to 0. Now, I would also like you to know that in logistic regression, in addition to the Wald's test statistic, we also have other test statistics such as the likelihood ratio test statistic. What is the likelihood ratio test statistic? The likelihood ratio test statistic compares the likelihood of the full model and the reduced model. What is the reduced model? The model for the null hypothesis. What is the full model? It's the model for the null and the alternative combined. So to get the likelihood ratio test statistic, we have to first maximize for beta hat under the full model and then maximize the likelihood under the reduced model. Minus 2 log of this likelihood ratio test follows the chi-square distribution. So naturally, the chi-square test statistic is nothing but twice log of likelihood maximized under the full model minus 2 log likelihood maximized under the reduced model, converge to the same distribution. So as we have learned in the previous class as well, we can use the predict function to predict whether the market will go up and down. Now there is one more thing that I would want you to know, which is the confusion matrix. What is this confusion matrix? This is a categorical feature with two classes, up and down. So in the actual observations, there are some ups and some downs. we need to understand that in the predicted, if the ups have been predicted as up and the downs have been predicted as downs or not. If the ups have been predicted as ups, then we call it true positives. And it's a situation where we do not have to worry. Similarly, if the downs have been predicted as downs, we call them true negatives. But if some of the downs are predicted as ups, then those are false negatives. Similarly, if some of the ups have been misclassified as down, then those are false positives. Of course, the false negatives and false positives are the ones which we have to be worried about. So after performing logistic regression, we can look at this confusion matrix to understand how good our prediction is. So here you can see there are 145 downs which have been predicted as downs. So these are our true negatives. Similarly, 507 ups have been predicted as ups, and these are our true positives. However, we have the false negatives and also the false positives. So we can calculate the amount of accuracy by looking at the number of false positives and false negatives out of the total number of predictions. And that would give us a measure of accuracy. So as you can see, this particular model only has about 47% or slightly less than 50% rate of accuracy. So as you can see, this particular model using the p-values also did not give us very significant results. Looking at the null deviance and the residual deviance difference also, this model did not seem to be a significantly useful model, and from the accuracy point of view also, accuracy doesn't seem to be very high. It's just close to 50%. So to have a better model, we may include other features, or we may also consider dropping some of the features and explore how the model improves. So this is just another example to understand the different outputs in R. Now let us wrap up the session on logistic regression. So here we have tried to understand that whenever our target feature is categorical, we cannot pass a regression line through it. Hence, least square estimation may not be a feasible estimation procedure for modeling a categorical Y. We have also understood that we cannot use correlation coefficient anymore to calculate the amount of association between two categorical features. So for that, we needed to learn one new measure called the odds ratio. And we have seen whenever log odds ratio is positive, it indicates a positive association between the two features. If it is negative, it indicates a negative association between the two features. And whenever it is 0, it indicates that the two features of interest are independent. We have also seen that testing for the log odds ratio equal to 0 is the same as testing for the logistic regression coefficient to be 0. Or in other words, if we want to know if a particular predictor variable has any effect on our target feature, which is categorical, we can either test the log odds ratio or we can also test the regression coefficient of the logistic regression. For that, we can use the Walls test or also the likelihood ratio test. We have seen the implementation also in R. So even though log odds ratio is very convenient, still we will need to use logistic regression because sometimes y is not a simple binary feature. It can have more than two categories. Also, it may be dependent on multiple predictor features. That's when logistic regression comes in handy instead of calculating the odds ratio for all of these combinations. To run the logistic regression in R, we need to mention family equal to binomial, and also if we want the link logic as the required link function. However, please note, if we are already mentioning family equal to binomial, logit link is the default link. And why are we using the logit link? Because in logistic regression, we are not directly modeling our y's on the x's. Rather, we are modeling the log of odds of y on the different predictor sets. Since least square estimation is not feasible for logistic regression, method of maximum likelihood estimation is used for estimating the regression coefficients. We have also seen that over here in logistic regression that we cannot calculate the individual residual values or the R-square and adjusted R-square statistics. Hence, we need to use some other quantities called null deviance and residual deviance to understand as model selection criteria. Again, we can also use AIC or BIC also to choose among different models. Just like regression, smaller the AIC and BIC, better the model. For deviance also, smaller the amount of deviance, better the model.